Before we write our first monetary policy, our first minting policy, let's briefly recall how validation worked that we have seen so far. So when we don't have a public key address, but a script address and a UTXO that sits at such a script address and a transaction that tries to consume that UTXO as an input, then for each such script input, the corresponding script is run, the validation script. And that validation script as input gets the datum, which comes from the UTXO, the redeemer, which comes from the input, and the context. And here we can see the context again. Recall that's in package Plutus -ledger -API as well in the module plutus.v1.ledger.context. And so it's defined here. And it has two fields, the txinfo field and the script purpose field. And we saw that for script purpose, everything we have seen until now always had the purpose spending txoutref, where txoutref is a reference to the UTXO we try to consume. And this txinfo has all the context information about the transaction that is being validated. Now for monetary policies, for minting policies, this is triggered if the txforge field, in this one here, txinfo forge, of the transaction contains a non-zero value. In all the examples we've seen so far, this was always 0, which means in the transactions we've seen so far, we never created or destroyed tokens. But if this is non-zero, so we have a value here, then this value, as we have seen just now, can contain a bag of asset classes, so different asset classes for different currency symbols and different token names. So if this is non-zero, then for each currency symbol contained in this value that is being forged, the corresponding minting policy script is run. So each currency symbol is the hash of a script, of a policy script, a minting policy script. And for each value that appears here, for each currency symbol that appears in this value in the forge field of the transaction, the corresponding script that belongs to the currency symbol is executed. And where the validation scripts had 3 inputs, the datum, the redeemer, and the context, these minting policy scripts only have 2 inputs, a redeemer and the context, no datum. That would make sense because datum sits at something that's being spent and the output. And in this case, there is nothing like that. There's no place where the datum could possibly sit. So the transaction will provide the redeemer, as it also provides the redeemer for all script inputs. So for each currency symbol in this value with a non-zero amount, the corresponding minting policy script will be run with the redeemer and with the context. So the context will get as txinfo the transaction that's being validated, and as script purpose it will get minting with the currency symbol that is currently checked. So whose minting or burning is currently checked. So in principle, in this forge field, in the value of the forge, there can be several currency symbols. And then for each of those, the corresponding minting policy would be run. And the purpose would change accordingly, so with the appropriate currency symbol. So let's look at an example of a minting policy. And let's start with a very simple one, similar to what we did for validators. I created a module free, and as for validators, we first define a Haskell function that represents the policy, and then we'll compile it to Plutus Core. So a validator takes the datum, the redeemer, and the context. And as I explained, there is no datum for policy, so we just have redeemer and context. And for this simple one as redeemer, we can use just unit. And then script context as before, and again bool. So this is the typed version. So I mentioned before that there's low-level Plutus, which just uses data or built-in data for all arguments, and then returns unit, and failure is indicated by throwing an exception. But we won't bother with that here and immediately use the typed version. And normally for the redeemer, I would need a isData instance, but unit has one already. So the simple-most policy we can write is the one that always returns true. So no matter the script context, we just return true. So this represents a minting policy that allows all sorts of minting and burning for the currency symbol given by this policy. Recall, the currency symbol is the hash of the script. Next, we have to compile this policy to PlutoScript. And I call it the result policy, so it's of type minting policy. And very similar to what we do for validators, there's a function called make minting policy script, and then comes template Haskell. And again, we use compile and Oxford brackets. And here it's slightly different to what we do for validators. So we take our policy, our Haskell function, but that still has to be converted to the untyped version that just uses built-in data for the arguments and a unit return type. And this is what wrap minting policy does. So as before, this wouldn't work because in these Oxford brackets, everything has to be inside them. So we can't have external definitions except if they can be inlined. So again, we have to add this inlineable pragma. So let's do that. Inlineable make policy. And once we have the policy, we can get the currency symbol by using the function script currency symbol applied to the policy. I should mention that similar to how we have parameterized validators, we can also have parameterized policies. So there could be additional arguments here in front of that, the parameters of the policy. So if I start the REPL and load that module, then the currency symbol should be available and I can actually look at it. So this is now the hash of the script that we got from compiling the Haskell function that represents the policy. So that's the first currency symbol that's not ADA that we see. Going back to the editor, this completes the on-chain part. So we define the policy as a Haskell function, compile it to PlutoScript, and we can also derive the currency symbol from that. But in order to try it out, we also need an off-chain part. So I prepared that already. And the idea is that we will have one endpoint called mint that takes as parameter the token name and the amount we want to forge, respectively burn. So if the amount is positive, we will forge, and if it's negative, we will burn. We only have to specify the token name because the currency symbol is given by this script. So the off-chain function in the contract monad, it takes these parameters. Then first we compute the value that we want to forge or burn. So we use the singleton function that we saw before. Currency symbol is our shining new currency symbol. And we extract the token name from the parameters and the amount. Then as lookups, we have to specify the minting policy. So the transaction has to contain the actual script, the minting policy, the policy itself, for validation to be successful. And the only constraint we put on our transaction is using something called must mint value, which is self-explanatory. So this transaction must mint the value we computed before. Then when we submit, so when we use submit TX constraints with these lookups and that TX, then the algorithm will automatically take care to find an input in the wallet to cover the fees, and it will automatically transfer the minted value to the wallet if it's positive. If it's negative, it will try to find sufficiently many tokens in the user's wallet that can then be burned. So we wait for confirmation and log a message that we forged this value. So then we define the endpoints as before. So we just call mint and then recursively endpoints again. And mint prime is just using our mint, but using the endpoint function to actually expose an endpoint and then feed the parameters using bind into the mint function. So this is boilerplate so that we could try it out in the playground. And additionally, I also defined an emulator trace. Since the last lecture, we know how to do that, so we don't have to test it in the playground. We can also just run it on the console using emulator trace. So I define a token symbol, TN, token name. Then I run these endpoints, so the endpoints contract in wallets 1 and 2. So I start them. Then I call the endpoint mint on wallet 1, where I use this token name and I mint 555 coins of that token. Then wallet 2 mints 444 coins of that token. I wait one slot, and then I, on wallet 1, burn 222 tokens. So in the end, wallet 1 should have 333 and wallet 2 should have 444. And I wait another slot. I should still mention that here in the must mint value function, I'm just mentioning the value and not the redeemer. And that is because the case that the redeemer is of type unit is very common, so there is special treatment for that. Let's try this out in the REPL. I have to reload. Let's try it out. And we see in the end, indeed, wallet 1 now has some ADA, a bit less than before because of transaction fees, and indeed 333, this currency symbol and that token name. And wallet 2 has 444. So as expected. Let's now try out the same scenario in the playground. So 2 wallets and the beginning both mint. Then we wait for 1 block and then wallet 1 mints again, or rather it burns, but of course the endpoint is the same. And another wait action. So token name was ABC. And 555, 444, and minus 222. Okay, let's see. Okay, so as always, the Genesis transaction distributing the initial funds. Then here we have our 2 mints. This is the one by wallet 2. So the UTXO coming from the Genesis block goes in to pay for the fees, which in this case are 8,027 Loveless. Wallet 2 gets the change, and wallet 2 gets 444 of this newly minted tokens that didn't come in. So they have really been forged in this transaction, as is also indicated here in this forging block. This is the same for wallet 1, exactly the same, except everything is for wallet 1, and it's 555 instead of 444. And finally, this should be the burning by wallet 1. So in goes some ADA to cover the fees, and the UTXO we got in the previous transaction with the 555 tokens. Then in the forge field we see the minus 222, and so the fees are paid, and the change and the rest of the token go back to wallet 1. And we also see that wallet 1 ends up with 333 and wallet 2 with 444 of those tokens. So the same result that we saw in the emulator trace. So this concludes a complete walkthrough of our first monetary policy script, one that doesn't put any restrictions on minting or burning. And we saw in our simulation and in the emulator trace that indeed wallet 1 and 2 can both mint the token. And we also saw that wallet 1 can burn it again, but of course wallet 2 would also be able to. So this is a maximally permissive policy that doesn't impose any restrictions. Anybody can freely mint and burn. Any transaction can freely mint and burn.